Okay, let's start this session. This is the last one, but not least. That we know that we are standing between you and the dinner. We will be quick, but I guarantee you it was the time. So this is Xin. I'm from the Sonic Outreach Committee.
My name is Sunny Tsai. I'm Marketing Manager for Sonic Foundation.
Yeah. In this session, we are going to introduce the 2023 Sonic Hackathon winners result. But before that, I would like to introduce that we have 19 teams participated in this year's Sonic Hackathon. A lot of innovations, and everyone, actually, I would say that to shed the spotlight on them, because they are all innovators, no matter winning or not. So they are tackle different problems. Some of them are pain point in the community or in the source code. Some of them are more far-reaching thinking. So with that, and also we would like to thank 7 judges from different companies, put their time to evaluate them, to ask questions. Okay, let me stop here for 30 seconds, because you might be interested in these topics. We will see they come to the community to contribute to the code back and idea back. Monitoring, security, counters, also toolings. Okay, with that, let's go to the first winner.
All right, thank you, Xin. So given the large number of proposals that we received, the judges have determined 3 winners for the 2023 Sonic Hackathon. The first winner is Sonic Stack Overflow Log Analyzer Tool from NVIDIA. Let's give a quick round of applause to the team from NVIDIA.
If you have team here, please stand up.
Well, this video will be played to the NVIDIA team and the community members. So
expectation, we are going to play 3 short videos, each one 5 minutes only. Give you a highlight, what's the idea, what's the demo of this hackathon. It's going on. It's okay. The beginning does not have sound.
Hi, my name is Marian Kutzak, and we are a Sonic team at NVIDIA. We would like to present to you today our idea for improving the development workflow in Sonic community called Sonic Stack Overflow. Let me present the challenge, the regression analysis workflow. Nightly regression pipeline is executed automatically during the night. Then the working day starts, and a developer on duty has to check regression, find that some tests failed, analyze test logs manually, and other system logs looking for and extracting errors. Then go over GitHub issues for possible fixes or ask community to help find them. Then apply fix also manually. If it's a known issue, then cherry pick fix to Sonic, or test, or skip test until issue is fixed. If the error is new, open an issue in GitHub. So here's the problem. Native GitHub search is inefficient. Allows only exact string match, cannot search multiple error messages at once. Error message is not linked to a Sonic code. Which requires us to perform extra search in the code to find who printed that inside the commit that was running regression. Raising an issue for failed tests. This is also repetitive manual labor, requires to fill in the template with the data from a test, which is equal to moving data from one place to another. And you have to repeat everything from above for every test failed. So we want to automate that and provide an ability to Google the issues. We propose a better way to automate the repetitive and repetitive everyday Sonic regression work called Sonic Stack Overflow. Sonic Stack Overflow is a service that can be embedded into regression pipeline running Sonic management tests. It has intelligent search provided with Elastic Search Engine. For example, if error message contains Ethernet 4 but GitHub issue has Ethernet 16, it will still be found. Multiple suggestions per error message ordered according to relevance. Sonic Stack Overflow will search within the issues to find a PR and version that possibly contains a fix. Automated GitHub issue templates. Sonic Stack Overflow will provide a link to open a new issue in Sonic GitHub. An issue will contain error logs, link to the code that generated error messages, and tech support attachment. And here's the improved workflow. Nightly regression pipeline is executed automatically again, but this time Sonic Stack Overflow filters errors from the logs, runs a custom search over indexed GitHub issues, and writes a prescription for each test for a specific action to be taken. All you have to do is check regression, find that some tests failed, look at the prescription for analysis and recommendations. Decide according to prescription, which contains either a pointer to a PR with a fix or an already existing issue, or a link to automatically create GitHub ticket if no fix is available. And now, demo. So we start by running Sonic management test. So it goes as usual. You can see that there is some configuration done to the switch. We have a live log from the test setup, and at some point it will fail. As usual, the entire test report is uploaded to Allure, but this time with Sonic Stack Overflow prescription appended at the end. So let's go ahead and open it. Here's our test report, and at the end you can see first two things: the error messages that were found in the failed test and the Stack Overflow analysis. So first, it's the list of most relevant issues to this list of errors. So let's go ahead and open the first one. You can see that we found that issue already existing in GitHub. And although it happened for example, here, the setup with the IPv6 addresses, we were still able to find it and match to our logs that have IPv4 addresses. But in case that it's not what we're looking for, here is a link to create a new issue that will do everything for you. You just need to basically click it. And what you'll get is a created issue in GitHub that contains these same logs, along with the error messages, a table with the error messages and the location encode for the relevant commit ID that was actually running in the regression. So you can see that this is the error log and its place in the code. So that's it. This is the demo for the Sonic Stack Overflow, which is intended to reduce time for repetitive work in Sonic community to improve our day-to-day lives and to provide an ability to spend more time on useful contributions. Thank you.
So this one is about the tooling, enable our developers to work more effectively or efficiently. The next one goes to Guohan team, that their innovation is about security Anyone from Broadcom team, you can stand up. Yeah. Congratulations. We also have a short clip for this.
Good morning and good evening, everyone. We, Team Sentinels, are here to present our hackathon entry, which is Sonic Secure Central. Let's jump right into the problem statement. Sonic today has no central framework to protect or manage sensitive data. User-configured protocol passkeys are stored in Redis DB in an unencrypted or plain text format. Also, components handle encryption and decryption of data independently if they need to, with possibly keys of different length and strength, and they could also be using weaker encryption algorithms due to the absence of a centralized framework. Also, in cases where components need to share sensitive data amongst each other, encryption and decryption of data will have to be handled independently by each component in the absence of a centralized framework. This is where Sonic Secure Central Framework comes to the aid. It is a framework developed for Sonic to protect sensitive information, and it provides encryption and decryption services via Python and C++ APIs that are usable across Dockers and host. It leverages the Linux system dbus infra for communication, and it offers a secure and centralized key generation and management mechanism. AES 128 CVC encryption is supported, and this AES key used for encryption is generated from the system MAC, which is used as a seed for PBKDF2. The infra is extensible to use a trusted platform module going forward, and there is also a possibility of user providing a custom seed string for key generation. This is generally useful in cases where multiple devices in the network need to use the same key to allow for config copy paste across devices. Let's now look at the SSE infrastructure overview. The SSE infra sits on the host and comprises of multiple building blocks as is seen in the diagram. The key file is saved on the disk, and it is only accessible to the root user. All the protocol applications sitting on the host or within the Dockers communicate with the SSE infra via the Linux system dbus. Let's now look at a sample flow which illustrates how the centralized SSE infra aids in seamless encryption and decryption of sensitive data. So here we see that the user configures a radius passkey via the CLI. The radius config handler talks to the SSE infra to encrypt the passkey, and then the encrypted passkey is written into config.db. On a write into config.db, host config.d, the daemon, wakes up and it tries to decrypt the radius passkey using the SSE infra. Decrypted passkey is now written into the radius config file in a plain text format. Let's now look at a short demo of the solution. We have a box here where a SSE key has been generated, and the key has been generated from the system MAC. Let's look at the key file now. So as you can see, the key is only accessible to the root user and is in the binary format. Let's now look at the radius configuration. There is no radius configuration on the system right now. Let's now just go ahead and add a radius server with a passkey configuration. What this would do is it will trigger encryption at the config handler and decryption at the host config.d. Now we'll see how the passkey is saved in the Redis DB. As is evident here, the passkey is in the encrypted format and is no longer in the plain text. Let's go back and look at the radius configuration file and see how the passkey has been saved. So here in the radius configuration file, the passkey is in the unencrypted or the plain text format. Let's look at the SSE logs right now. So the logs here show that SSC generated a default key during boot up, and when we configured a Radius server with a passkey, the config handler encrypted the Radius passkey with the help of the SSC infra, and similarly, host config D decrypted the same Radius passkey with the help of the SSC infra. Today we saw a specific protocol use case of the SSE infra. In reality, SSE infra can be used to protect sensitive data across the system, and hence it is a valuable addition to the Sonic ecosystem. Thank you.
Great. Last but not least,
Good morning and good evening, everyone.
we have the third winner is Team from Dell, Smart Sonic Monitoring System. Let's give a quick round of applause to the Dell team.
If we have people from Dell, feel free to stand up. Yeah. Congratulations.
I'm Ishanya, here with my teammates Shweta, Himanshu, Sai to present Smart Sonic Monitoring System, adding smartness to guard everyday Sonic using machine learning. All knows Sonic with its containerized architecture, open source nature, and capability to run on switches from multiple vendor and ASIC is becoming network OS of choice. But with its large-scale deployment in data center, its continuous monitoring and maintenance is a challenge. Most end users are unaware of the issue that might happen in the switches, and when a system crashes with heavy technical log, it causes panic in them. End user also are not aware whether an issue needs to be escalated to the maintenance or it's fault at their end. So they just keep posting their errors with the technical team. End users are also not familiar with the severity of an issue unless a crash occurred, and this crash could have been avoided if the issue was escalated timely. Discuss the design prototype. The system runs in two parts. One is the log parser running in the Sonic device. This parcel will run continuously and monitor for any critical error warning logs. These logs are then pre-processed and sent to the cloud server where log analyzer is being run in a JSON format. Here we are running two ML models. One ML model will predict the severity of the issue. Another ML model is used to predict the likely cause of the issue. Then this is redirected through SQL Server for their storage and to train again the ML model efficiently. And this data is then just presented to the user in a Grafana dashboard. Log parser will monitor for any error warning or critical code logs. Then it's pre-processed, and since the data is textual, it's converted into vector format using TF-IDF, and the feature dimension is high, so we have reduced it using PCA. Then we feed the data into two ML models. One model will predict the severity of an issue and mark it as critical and non-critical. Other will mark it as the likely cause of the issue in a user-friendly format. This data is then fed to SQL Server and visualized through Grafana dashboard.
Hi guys, this is the live demo. So this is our log parser file, which will take input as a syslog. So we have collected some logs. This will act as an input to log parser file. So we are just parsing it and we are storing it into the JSON format as per our requirement. If it is in error, warning, critical, then only we are writing it to the JSON format file. You can see the JSON format file. So these are the fields, 4 fields of the JSON format file. This will act as an input to log analyzer module. So in log analyzer module, we need to label the data so that we have stored it into the CSV. You can see the error message and the respective label, non-critical or critical. This will act as an input to analyzer thing. In analyzer, first module is TF-IDF. So TF-IDF is basically the feature extractor, which will give you the numerical vectorized format for the given data. So after calculation the TF-IDF, we are reducing the dimensionality using the PCA to 10. So whatever the result, it will be act as a input to our model. So we are building two models, which are NV Gaussian and logistic regression model. So NV Gaussian is giving the more accuracy. You can see the NV Gaussian model accuracy is 80.95% and accuracy of logistic regression model is 61, which is very low. So we are, as we saw, like we have predicted the severity of a model as a critical or non-critical using the TF-IDF and NV Gaussian and logistic regression model. So we are using the same model for to predict the class of an issue. So we have divided the error into the 5 classes, and we are using the same model. We already ran our program. You can see the accuracy of the NB Gaussian is 83, and accuracy of the logistic regression, which is also similar to the NB Gaussian. So we are giving the data to the dashboard also for visualization purpose. So here is the data. You can see the entry severity and issue are predicted by our model, and recommendation we are giving based on.
This is the Smart Sonic Monitoring Dashboard. We have Sonic logs with containers, error codes, predicted severity, and recommendations. And then we have a cumulative display of container related issue count and the number of critical and non-critical issues. And then we have the device management dashboard. Any new Sonic device deployed in the user environment will be onboarded here. Device related information such as the status, memory, and CPU utilization, location will be updated over here.
So with that, we thanks all the participants of this year's hackathon, and we're looking forward to next year. By the way, that we actually see many Sony community leaders, TSC members, outreach community, outreach committee members, and group leaders. If you could please stand up so people can get connected if you want to connect with them, like the audience. That we have TSC committees that I see multiple. Yeah, we have a community member like leads hosting meetings. I saw also board members but they left. But with that, actually, thanks everyone. Yeah.
And thank you, Anil, for emceeing today, and thank you, Xin, for helping with organizing the event.
Yeah.
Thanks
everyone. Yeah.